So how do we figure out something like the average lifespan of a star or whether a new drug actually works? I mean, we can't test every single one, right? Instead, we have to make a really good educated guess. And in this explainer, we're basically going on a quest to find the perfect guess using the amazing tools of statistical estimation. Think about it like this. Imagine you need to know the average height of every single person in the country. You can't possibly measure everyone. It's just not going to happen. So what do? You grab a smaller group, a sample. And that's the big problem we're trying to solve. We've got this one small piece of the puzzle, our sample, but we want to know what the whole picture, the entire population, really looks like. Okay, so how do we make that jump from a small group to everyone? We need a special tool, a mathematical way to make our best guess. In statistics, the hero of our story, the thing that does this for us, is called an estimator. An estimator is kind of like our detective's best guess. It's not just a random shot in the dark, it's a specific formula. It takes all the clues from our sample data and spits out a single number, our best attempt at figuring out the true value for the whole population. But what makes a guess a good guess? Well, a great estimator needs two key things. First, it's got to be unbiased. Think of it like you're throwing darts. Being unbiased means that on average, your darts are landing right around the bullseye. You're not systematically aiming too high or too low. Second, it needs low variance. This means all your dart throws are clustered really tightly together. The absolute best estimator is both. It's accurate and precise. So our mission is to find a guess that's both on target and super consistent. But how do we get there? We need a way to take all of our sample data and kind of boil it down into one single super powerful clue. We need an information shortcut. And that shortcut is called a sufficient statistic. It's this one value that you calculate from your sample that contains all the important information you need. It's like a perfect summary. Once you have it, you could literally throw the original data away and you wouldn't lose any key insights. It's that powerful. Okay, so we've got this super clue, this sufficient statistic. Now what? How do we actually use it to make our guesses even better? Well, believe it or not, there's a guaranteed recipe for it. This brings us to something called the Rao-Blackwell theorem. Now, it sounds super complicated, I know, but the idea behind it is actually pretty simple. It gives us a recipe to improve our guess. It basically says we can take any unbiased guess we have, combine it with our sufficient statistic, and out comes a new guess that's still unbiased, but has even less variance. It is a guaranteed upgrade for our estimator, every time. The whole process is really just a few steps. You start with any old unbiased guess you can come up with. Then you find that sufficient statistic, our super clue. And finally, you use the theorem to mash them together. And the result? You get a better, tighter, more precise estimator. It just works. All right, so this recipe is obviously really powerful. But what do you think would happen if we tried to get a little greedy? We've already improved our guess once. What if we try to run our new, better guess through the exact same process again, with the same sufficient statistic? Do you think the variance would shrink even more, making our guess even more precise? Or would it just stay the same, because there's no more improvement left to get? Go ahead and take a second to think about that. Feel free to pause and make your guess before we move on. The answer is nothing changes. The Rao-Blackwell recipe sucks all of the possible improvement out of that sufficient statistic in one shot. You can't squeeze any more juice from it. All that goodness gets baked in on the very first try. And this whole process leads us to the ultimate prize, what you could call the holy grail of our quest, the MVUE. That stands for Minimum Variance Unbiased Estimator. It's the absolute best of both worlds. It's right on target, and no other unbiased estimator is more precise. This is the guess we want because it gives us the most reliable information possible from our data. And that is so important for making smart decisions, whether it's in science or in business. Finding this MVUE is the goal, right? But that kind of brings up a new question. How do we even get our initial guesses in the first place? Well, there are two common ways to do it. And the first one is a really intuitive approach called the method of moments. The idea here is really simple. In statistics, moments are just properties of a data set. Like the average, that's the first moment, or the variance, which is related to the second moment. With this method, you just calculate these moments from your sample, and then you figure out what the population value would have to be for the population's moments to match your sample's moments. You're just matching up the puzzle piece to the bigger picture. Now, the method of moments has some pretty clear pros and cons. On the plus side, it's super easy and intuitive, and the guesses usually get better as you get more data. The downside? It often completely ignores our superclue, that sufficient statistic. And that means it can be inefficient and isn't always the best guess you could possibly make. So if the method of moments is our simple, straightforward path, there's another path that's more powerful, and honestly, often better, and that is the method of maximum likelihood. The way of thinking here is completely different. Instead of matching up moments, maximum likelihood estimation, or MLE, asks this really powerful question. Given the actual data I collected, what population value makes this set of data the most likely outcome? We're trying to find the value that maximizes the likelihood of what we saw. And finding this most likely value usually follows a standard recipe. You write out a function that represents the likelihood of seeing your data, and then you use a little bit of calculus to find the very highest point on that function's graph. That peak, that's your answer. It's the parameter value that makes your data the most probable. This method is incredibly popular, and for some really good reasons. First off, it automatically uses our sufficient statistics, which is awesome. It also has this really flexible property called invariance. And here's the big one. If a maximum likelihood estimator is unbiased, there is a very, very good chance it's that holy grail we've been searching for, the MVUE. So at the end of the day, we have two very different ways of thinking. The method of moments asks, what would make the whole population look like my little sample? While maximum likelihood asks, what population value makes my sample the most probable thing I could have seen? One is all about matching patterns. The other is about maximizing probability. They're just two different paths on our quest for the perfect guess. And that brings us to one last thought to leave you with. We've talked about how to create these guesses from one sample. But what happens as we get more and more data? How do these estimators act as our sample size gets bigger and bigger, heading towards infinity? Well, that's a story for another time.